Hello everyone, this is Dr. Sandeepar working as Associate Professor in the Department of ECE, Vidyavardhaka College of Engineering, Mysuru. Today's topic of discussion is Discrete Time Fourier Transform, in short represented as DTFT. Now this is a mathematical tool used to apply a transformation on a discrete and non-periodic signal, discrete and a non-periodic signal x of n into a corresponding signal, say x of omega, which is continuous and periodic. This x of omega is continuous and periodic. So DTFT is a mathematical tool used to apply transformation on x of n to obtain x of omega. Now if I want to get back x of n from x of omega, then I'll apply inverse discrete time Fourier transform on x of omega to get back x of n. So please observe, x of n is discrete and non-periodic, whereas x of omega is continuous and periodic. The equation used to obtain x of omega from x of n is called the forward transformation equation or the analysis equation. So x of omega is given by summation n is equal to minus infinity to plus infinity x of n into e power minus j omega n. This is called as the analysis equation. Or it is also called as the forward transformation equation. Now the equation used to obtain x of n from x of omega is called as inverse transformation, or also called as the synthesis equation. So x of n is equal to 1 by 2 pi integral for one complete cycle, that is 2 pi x of omega into e power j omega n and d omega. So this is the synthesis equation, okay, also called as the reconstruction equation or the backward transformation equation. Okay, the plot of x of n, so the plot of magnitude of x of omega versus omega is called as the magnitude spectrum. And the plot of phase of x of omega versus omega is called the phase spectrum. Together, the plot of magnitude of x of omega versus omega and the plot of phase of x of omega versus omega is called as the frequency spectrum. And if you try to plot the magnitude square, so I take x of omega magnitude and I square it versus omega, then I get the energy spectrum. Now we have told that x of omega is continuous and periodic, right? And we shall prove that now how it is periodic. But before that, we had told that yes, DTFT is a mathematical tool used to apply on discrete and non-periodic, but we will see in our later lectures that DTFT is also applicable on discrete and periodic signal. I repeat, it is also applicable on periodic signal. How we shall do that, we will see that later. But for time being, we'll assume that yes, it is applicable on discrete and non-periodic signal. The other conditions that has to be taken care of is that the discrete time discrete time non-periodic signal x of n should be a converging sequence, or it should be an absolutely summable. Only if it is absolutely summable or if it is converging, only then I can apply discrete time Fourier transform on x of n. Otherwise, if it is either a diverging sequence or if I cannot sum it and if I don't get a finite number, then I cannot apply discrete time Fourier transform on x of n. Okay, now we shall see that is really x of omega periodic. If it is periodic, what is the periodicity? We know that it is periodic with period 2 pi. Let's try to prove that. What we are trying to prove now, that x of omega plus 2 pi is equal to x of omega, that is, it is periodic with period 2 pi. Let us see that. For that, let us use the analysis equation. We know that x of omega is given by summation n is equal to minus infinity to plus infinity x of n into e power minus j omega n. Okay, now let us try to replace wherever omega is there, replace it with omega plus 2 pi. Let us see what do we get by doing that. Now x of omega plus 2 pi is equal to summation n is equal to minus infinity to plus infinity x of n into e power minus j omega plus 2 pi into n. Okay, now let us consider it on the right hand side. Using laws of indices, the summation n is equal to minus infinity to plus infinity x of n. Using laws of indices, I can write this as e power minus j omega n into e power minus j 2 pi into n, or 2n pi. So let us see what is this e power minus j 2n pi means. So using Euler's identity, I can write this as cos of 2n pi minus j into sine of 2n pi. Okay, if you observe, n can be 0, 1, 2, minus 1, minus 2 and so on, integers, right? Now for all that, into 2 I'll get an even, and sine of any pi is always 0, so this is 0. Now what about this n being an integer? 2n will give me an even number. Cos of even pi is always 1, so this is 1, and hence 1 minus j 0 is nothing but 1. So this entire thing, this will get is equal to 1. This entire thing is 1. So what are we left out with? We are left out with n is equal to summation n is equal to minus infinity plus infinity x of n into e power minus j omega n. This is 1 into 1. So what is that equal to? Which is nothing but, it is x of omega. LHS we have x of omega plus 2 pi. On the right hand side we have got x of omega. So we have proved that x of omega plus 2 pi is equal to x of omega. In other words, the discrete time Fourier transform is representation is continuous and periodic with 2 pi. Okay, let us try to see some examples by applying discrete time Fourier transform on some basic signals. Say, let us consider x of n is equal to delta of n. So this is discrete version of an impulse function. What is delta of n given by? Delta of n for a discrete time, delta of n is equal to 1 only at n is equal to 0. It is 0 for n not equal to 0. So if I plot it, say this is n discrete, 0, 1 and 2, minus 1 and minus 2. So only at n is equal to 0 it will have the value, and it is 1. So this is 1 and this is delta of n. So we are trying to obtain the discrete time Fourier transform on this particular signal. So step 1, we will write the formula. So x of omega is given by summation n is equal to minus infinity to plus infinity x of n into e power minus j omega n. e power minus j omega n. So kindly excuse me for this handwriting. Yeah, okay, e power minus j omega n. Now we know, using the definition of the discrete time version, I can write this as, okay, so substituting that, summation, so n is equal to minus infinity to plus infinity, x of n is delta of n into e power minus j omega n. Okay, now delta of n exists only at n is equal to 0, correct? And for n not equal to 0, it is 1. So this exists only at n is equal to 0. For all other values, it is 0. At n is equal to 0, what is its value? 1. So this entire thing, so this is 0. So this function, so we had learnt in the earlier classes that x of n into delta of n is given by x of 0 into delta of n, correct? Okay, so this function gets evaluated at n is equal to 0. Now accordingly we have to evaluate this function at n is equal to 0. So evaluating this function at n is equal to 0, it will result in 1, and delta of n is equal to 1 at n is equal to 0. So entire thing gets evaluated as 1. So in other words, delta of n is the time domain representation and the frequency domain representation is 1. So this is x of n and this is x of omega. So how do you plot the magnitude and phase spectrum? The magnitude spectrum, so this is omega, and this is magnitude of x of omega, and it is 1, right? So we have to write for one complete cycle. So from minus pi to plus pi I write it, and it is 1, and it is 1 for minus pi to plus pi. What about that? It repeats, it is continuous and periodic, right? So we have written only for one complete cycle. And what about the phase spectrum? The phase spectrum is given by, say, omega and phase. So this is phase x of omega. We know that this 1 can be written as 1 at an angle 0, right? So in polar representation, so magnitude is 1, phase is 0. So in other words, phase is 0. So phase is 0 from minus pi to plus pi. So this is 1 at an angle 0. That means what? See here, another concept that I need to include here is that in time domain you can see that the support of the signal is very narrow. That is, it is present only at n is equal to 0. So it is very much compressed in time domain. What is the corresponding representation in frequency domain? You can see that it has got a frequency representation and it exists from minus pi to plus pi magnitude, and phase is 0 from minus pi to plus pi. But you can see that it is existing for all possible values of omega, taking the values from minus pi to plus pi. So it is expanded. So compression in the time domain leads to expansion in frequency domain. So we can take that concept here, and you can say that here it is compressed, but here it is expanded. So compression in time domain leads to expansion in frequency domain. So it is expanded. So expansion, compression in time domain leads to expansion in frequency domain. Let us see another example. We can see that, say, what will happen if I consider the time shifted version of the impulse function. So let us consider that x of n, now it is equal to delta of n minus 1. What is delta of n minus 1 defined as? Delta of n minus 1 is defined as, it is equal to 1 only when n minus 1 is equal to 0, or when n is equal to 1, or it is 0 when n minus 1 not equal to 0, or when n is not equal to 1. So plotting it, how will it look? So this is, say, n discrete time signal. I am plotting discrete time signal x of n, say at 0, at 1, at 2, at minus 1, at minus 2. This function exists only at n is equal to 1 and its value is 1, correct? At n is equal to 1. So this is the function that is given to us. Now we have to obtain the discrete time Fourier transform representation of that. Following the same lines, I can write x of omega is equal to summation n is equal to minus infinity to plus infinity x of n. Now what is x of n? We'll straight away write delta of n minus 1 into e power minus j omega n. Now we know that x of n into delta of n minus n naught is equal to x of n naught into delta of n minus n naught. So that means what? We know, because we know that this function exists only at n is equal to 1. This only exists at n is equal to 1. So we have to evaluate this function as per this property. X of n into delta of n minus n naught is equal to x of n naught. So we have to evaluate x of n at n is equal to n naught and into delta of n minus n naught. So this function has to be evaluated at n is equal to 1. So evaluating that, we get it as e power minus j omega. And what is the value of delta of n minus 1 at n is equal to 1? It is 1. So entire thing results in, so because the value exists only at n is equal to 1. What about n is equal to 2? It is 0. What about n is equal to minus 2? It is 0. What about n is equal to 0? It is 0. For all values of n, it is 0. Only at n is equal to 1 it exists, and it is 1 into e power minus j omega. So it is 1 into e power minus j omega, or we can write this as 1 at an angle of minus omega in polar representation. So in other words, we can see that the time domain signal was delta of n minus 1 and the frequency domain representation was 1 at an angle of minus omega. So this was x of n and this was x of omega. So plotting it, we can see that x of omega, the magnitude spectrum. So now I am plotting the frequency domain representation. This is omega, magnitude of x of omega. Again it is say 0 and this is pi and this is say minus pi. It is 1, magnitude is 1, magnitude is 1. So you can see that magnitude is 1. And for, let us try to plot the phase representation. So omega, phase of x of omega. So 1 at an angle of minus omega, right? So we can plot this as from minus pi to plus pi. So it will be like this, straight line passing through the origin with negative slope. So this will be the way the magnitude and phase spectrum looks like. Even here you can see that in time domain it is compressed, whereas in frequency domain it is expanded, because it is existing for all values of omega ranging from minus pi to plus pi. So compression in time domain leads to expansion in frequency domain. Another concept that we can learn here is that when we worked about the first example, it was x of n is equal to delta of n, and the second case was x of n is equal to delta of n minus 1. So you can see that when I had got delta of n, the frequency domain representation was 1 at an angle of 0. When I had got delta of n minus 1, the frequency domain representation was 1 at an angle of minus omega, or 1 into e power minus j omega. So I can say that shift in time domain leads to multiplication by an exponential in frequency domain. Similarly here we can have delta of n plus 1 will have the frequency domain representation as 1 at an angle of omega. So in general there's nothing but 1 into e power minus j omega. So there's nothing but 1 into e power j omega. Both means the same. So shift in time domain corresponds to multiplication by exponential in frequency domain. So we'll stop at this. We will see what we can do with DTFT on some of it by taking some more examples in the next video. Thank you.